Good morning, one and all. Today I am here to give a presentation on how NASA used the rocket on the topic of rocket missiles and technology. Abstract. After 18 months living and working on the surface of Mars, a crew of 6 explorers board a deep space transport rocket and leaves for Earth. No humans are staying behind, but work goes on without them. Autonomous robots will keep running a mining and chemical synthesis plant they have started years before this first crewed mission even set foot on the planet. The plants produce water, oxygen, and rocket fuel using local resources, and it will be built up all the necessary supplies for the next year mission, set to arrive in the next 2 years. Officially, it's known as the ISRU system, but we like to call it a dust to trust factory, because it turns simple dust into rocket fuel. By some estimates, to ship a single kilogram of fuel from Earth to Mars, today rockets need to burn 225 kilograms of fuel in transit, launching into low Earth orbit, shooting off towards Mars, slowing down to Mars into get into Mars orbit, and finally slowing to a safe landing on the surface of Mars. We would like we will start with 2 226 kgs and end with 1 kg, which makes for a 226 is to 1 gear ratio, and the ratio stays the same no matter what we ship. We would need 225 tons of fuel to send a ton of water, a ton of oxygen, or a ton of machinery. The only way to get around that harsh arithmetic is by making our water, oxygen, and fuel on. NASA is focusing its attention on the moon. Most of the equipment will be tried out and fine-tuned on the lunar surface first, helping to reduce the risk of sending it all straight to Mars. It most often just volcanic rock that has been crushed over time into a fine powder, and on Mars a layer of rusting iron minerals that gives the planet its famous reddish, like a thick layer of a silicate with name like phosphorine, which are made up of silicon and oxygen structures bonded to metal like iron, aluminum, and etc. Dust to trust. Evacuating this material is challenging because its consistency and compactness varies from place to place on Mars. But what makes the task even harder is the planet's low gravity, which makes it difficult to score a shovel into a ground without using a weight to counteract the force. On Earth, we can dig that we often use large vehicles because its heavy body reacts appropriately to a force of the much smaller dig bucket. But remember the gear ratio problem. Even ounce that we launch to Mars is precious and very costly. So we had to figure out a way to dig on the surface of a Mars using very lightweight equipment. Enter Racer, a autonomous mining vehicle designed for one specific purpose: to dig or evacuate the layer in low gravity conditions. Robot evacuates consist of motors, gearbox, and other mechanisms that end up being a large percentage of the final mass of the system. In our design, we used frameless motors, electromagnetic brakes, and 3D printing titanium housing, among other things, to minimize weight and volume. To dig, Rajar used two opposing bucket drums, each outfitted with several small and 2D digging scoops. Another key feature of Rajar is that while digging the bucket, drums actually spin in opposite direction. This cancels out most of the digging force and will allow Raja to evacuate in low gravity. Once Raja has filled up its bucket's drum, it raises its arms and drives to a processing facility to underload the geolith. The robot simply spins the drums in reverse, and and the zeolite pours out from the same small scoop that is entered. Another piece of equipment, a robotic hopper, lift arm handle the next task is hoisting a load of zeolite. The answer is complicated. It depends mostly on where you dig and how deep you dig. Some areas on Mars seem to nearly solid sheets of water rise just a few feet below the surface. At some low latitude, the gypsum sand dunes consist about 8 to 8% of water by weight. When stripping of the water, the regolith is dumped on the ground so the Raja robot can scoop it up and haul it away. This waste material can actually be used for construction of primitive structures or even rods using 3D printing method now developing under NASA. Water. All the water that is pulled from the zeolite is then purified. The cleanup module process employs a multi-staging filtration system along with several deionized beds. The water isn't just for drinking, it's also the key ingredient for rocket fuel. By splitting the H2O molecules with the electrolysis into hydrogen gas and oxygen gas molecules and then compressing and liquefying both of these gas separately, we can synthesize the fuel and the oxidizer that are most commonly used in liquid fuel rocket engines. The problem is that liquid hydrogen must be stored at extremely low temperature. That's why NASA plans to turn the hydrogen into a type of fuel that is easier to store, that is methane. You can get it by combining hydrogen with carbon. But where do we go? You get the carbon on Mars. Luckily, the planet of Mars is composite totally with carbon. So we don't need to find the carbon around it because the the composition of a Mars is nothing but the carbon. Next, the next piece of equipment in our factory is an robotic and unbreakable arm for transferring fluid to an external tank. What is unusual about this system is that its umbilical is specifically designed to carry out dust. Residual dust is very fine and it gets into everything. And because residual is composed of crushed volcanic rock, it is very abrasive and quite hard on equipment. So keeping it out of unbreakable electrical and fluid connectors and any sensitive electronics is critical. Each side of an umbilical contains a set of doors that act sort of like an airlock to keep out the dust. Completing a connection requires three separation. Uh, this is the this is the figure of a robot in which it it does the process total. And next, this is the mining process of a Mars in which it consists of this sector. This is the figure of which it open. That's it. Thank you.